Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6. We'll be presenting about our data science group project titled Ensuring Water Quality for Human Consumption, a comprehensive data analysis. Before we start, I would like to introduce to you our group members. Our team consists of 5 members. Me myself is Hazim Imran bin Abdul Aziz. We also have Wisebo Abdul Majid, Muhammad Khairunas bin Nurizam, Haras Nasrullah bin Suhairul Afzan, and Muhammad Nurzahin Salihin bin Muhammad Hanafi. For introduction of our project, ensuring safe and clean drinking water is essential for global health and economic stability. Despite advancement, many still lack access to potable water, causing health and financial challenges. This research addresses the prediction problem of assessing water potability based on quality parameters like pH and contamination levels. Focusing on the business and public health domains, it aims to develop a classification system that predicts whether water is potable. This system can help business in water distribution and treatment ensure regularity compliance, enhance operational efficiency, and improve consumer safety.
Assalamu alaikum wa rahmatullahi wa barakatuh. Now, let's get a little bit of background knowledge on this. My name is Wisab Abdul Majid, and welcome. Throughout history, humanity has been seeking for clean drinking water. So we have to recognize its vital role in survival. Ancient civilization, let's say like the Roman civilization, have been the pioneers of innovations such as aqueducts, while filtration techniques emerged in early societies to ensure like the water safety. So, moving a little bit on 19th century, it marked a revolution with the advent of chlorination. And for the ones that don't understand what chlorination is you've been to a swimming pool, the weird smell that you hear, that's chlorination. It was a game changer in reducing the waterborne diseases. However, industrialization and urbanization brought new challenges like pollution, overuse, climate change, which now threaten the global water resources. So key indicators, let's say like pH, which must remain between 6.5 and 8.5, ensure that the water is safe to drink, while turbidity warns of potential contamination before it happens. So historically linked to outbreaks, these parameters are very crucial in modern water quality monitoring. So today we will use advanced data analytics for real-time monitoring and predictive insight, and also actionable strategies. This will align with the Sustainable Development Goal 6 or SDG 6, which envisions clean water and sanitation for all. So, by exploring these historical and technological advancements, we'll merge them so we can continue the legacy of securing water for future generations.
For problem statement of our analysis of our group project, we have 3 problems. The first is challenge in ensuring drinking water safety. Despite advancements in infrastructure, ensuring safe and potable drinking water remains a significant global challenge. Number 2 is underexplored pH potability relationship. The link between pH levels and water potability is insufficiently studied, especially in rapidly urbanizing and rural regions. Number 3 is overlooked role of pH in water safety. Water quality monitoring often neglects the critical role of pH as a key parameter for assessing drinking water safety.
So there will be three research questions in this research project. So the first one will be: is there any specific pH range that correlates strongly with potable water? The second one will be: how does pH level interact with other water quality parameters such as turbidity, hardness, or contaminant to affect water potability? The third one will be what variables lead to pH fluctuation in water sources for human consumption. So for our research objective, there will be three also. So the first one is to determine the relationship between pH levels and water portability, and also to identify whether a specific pH range is strongly correlated with portable water. The second one will be to analyze the interaction between pH levels and other water quality parameters such as turbidity, hardness, and contaminant, and also evaluate how these interaction affect water potability. The last research objective is to identify the variables that lead to pH fluctuation in water sources for human consumption. In this research, we made three hypotheses. So the first hypothesis that we made is that a specific pH range from 6.5 to 8.5 is strongly correlated with water potability. So this one is underscoring its critical role in establishing water quality standards. So the second hypothesis that we made is that the water samples with neutral pH and low contaminant level will exhibit the highest potability rates. So this one is emphasizing the importance of pH balance and contaminant reduction in ensuring water's suitability for consumption. So for the last hypothesis that we made is that the fluctuation in pH levels in water sources are significantly influenced by key water quality parameters such as hardness, solids, chloramine, sulfate, conductivity, organic carbon, trihalomethanes, and turbidity, each contributing uniquely to pH stability and water potability.
There are a few research significance for our group project. This research significance is important to this study because it contributes to the broader fields of knowledge. The first research significance is enhancing water quality management. This study analyzes the link between pH levels and water potability to enhance water quality management. Understanding safe pH ranges can help set clearer standards and improve monitoring practices. Number two is public health impact. Findings will identify areas at risk of unsafe water, help prevent waterborne diseases, and improve sanitation, supporting global health goals like SDG 6. Number three is supporting policymakers and environmental scientists. The research provides valuable data for policymakers, scientists, and public health officials to improve standards, regulations, and interventions for better water quality.
Welcome again. We say Abdul Majid here. So, in examining the body of research from 2019 to 2024, there is a clear emphasis that comes from the using machine learning techniques to address the critical issue of water quality production. So, among those techniques, there is algorithms such as random forest, support vector machines or SVM, and SGG boost that have been widely utilized. And they achieve remarkable accuracy levels in predicting water potability. So NN or neural networks have also been explored, particularly in heading like complex and large data sets. However, the literature revealed some key gaps. Few studies extend the scope beyond prediction to include like prescriptive analytics, which would provide actionable insight for decision makers. But the potential of hybrid models remain largely untapped, leaving like room for innovation, or as they call them, ensemble models. So these observations guided our research, which aim to bridge these critical gaps and push the boundaries of existing methodologies. So when we dive deeper into the comparative performance of techniques, ensemble methods such as random forest or gradient boosting emerge as the most like reliable performance, achieving accuracy levels up to 93%. And the advanced deep learning models, including CNN, LSTM, have pushed this further to 94%, which shows the capability to handle temporal and spatial patterns in water quality data. Despite all these successes, significant challenges remain, and many of these models are seen as black boxes because they lack interpretability for stakeholders who need to trust and act on the inside. And additionally, like integrating these models into real-time water monitoring systems remains very complex or very difficult. So our research seek to address these challenges by introducing a hybrid framework that marries predictive precision with prescriptive analytics, which offers not just what is likely to happen, but also actionable recommendation to improve outcomes. So our research goal is to go beyond the conventional predictive approaches found in existing studies, and we will do that by incorporating prescriptive analytics, a dimension that has been underexplored but hold immense potential. So this addition transform prediction into actionable insight, which guide the policymakers and businesses like stakeholders in making it data-driven decision to improve water quality. Aligned with the UN Sustainable Development Goal 6 or SDG 6, this work will hold a practical impact on global water management, particularly in region where access to safe water remains a pressing challenge, like Africa and all this part of the world. So we'll address the gaps in the interpretability and also the real-time application. Our research position itself as a meaningful contribution to the scientific community and also society. It fosters the future where every individual has access to to clean and safe drinking water.
Assalamualaikum, my name is Muhammad Harunas. For this project methodology, the research process are: first, data collection and pre-processing; second, exploratory data analysis; third, hypothesis testing. For the dataset, we use water potability dataset with attribute pH, hardness, solids, chloramines, sulfates, conductivity, organic carbon, trihalomethanes, turbidity, and potability. We've designed around 3,300 records. The tools to develop this project are Google Colab and R, with libraries deployed for designing data manipulation and transformation; ggplot2, which a visualization library used to create plot and graph; choroplot, which typically used to visualize correlation matrices; moments, which focus on statistical analysis of data distribution; and CAR, which support applied regression analysis and diagnostic tasks. Next is the machine learning algorithm that we use is linear regression, and the mathematical equation is pH equal to B0 stands for intercept, B1 through B8 times attribute, which stand for coefficient for the respective predictor, and plus epsilon, which stands for error terms. The performance measurement: first, R squared, which measure the proportion the variance explained by the model; adjusted R squared for the number predicted in the model; p-value for coefficient, which tests the statistical significance of each predictor; and multicollinearity check, which the variance inflation factor is calculated to detect it. Then, statistical tests that we use are: first, chi-square test to examine the association between pH range and potability; water potability rates under specific condition; contingency table to calculate the chi-square statistic; second, skewness analysis is compute to evaluate its distribution and determine the needs for transformation; and third, residual analysis, which linear regression assumptions are checked using diagnostic plot like residual versus fitted value, normal QQ plot, scale location plot, and residual versus leverage plot. Next, we do data preprocessing to clean the dataset. The initial data review found solid columns exhibit abnormal value, and found pH, sulfate, and trihalomethanes columns have missing value. Then, missing value percentage are calculated for each column, and none of these columns exceed 50%, and it did not drop. Next, the pH, sulfate, and trihalomethanes show normal distribution, which means the missing value can be replaced with mean imputation of their column. Then, in data preprocessing, we analyze outlier and skewness of solid column because we detect large gap between third quartile and maximum value. So, we plot box plot and bar graph to confirm the extreme outlier and right skewed distribution. For skewness transformation, we attempt to use log transformation, but it is ineffective. Then we use square root transformation and successfully normalize the distribution. After all that, original solid and solid log columns are dropped. Lastly, in the data preprocessing, portability column conversion. Portability initially treated as continuous variable, then we convert it to categorical factor for accurate analysis and visualization. This is to ensure compatibility with tools like ggplot2. And the final outcome is missing value is imputed, outlier addressed, and skewness reduced. With this, dataset is ready for in-depth analysis and machine learning modeling.
Assalamualaikum warahmatullahi wabarakatuh. My name is Zahid and I will present the result and discussion for our research on this data set. So for the water, we see that we have three hypotheses for our results. First is specific pH range, which is normal between 6.5 to 8.1, is very strongly correlated with water potability. So is it supported or not? It is supported. Why? Because when we perform the chi-square test, we got the p-value less than 0.05, which is the common significance. While for the H2, water sample with neutral pH and low contaminant levels will exhibit the highest potability rates. This is, however, is partially supported because neutral pH and low levels of specific contaminants can produce varying result. So either they will produce a high result or a low result for potability rates. So the last one is fluctuations pH levels are influenced by temperature, contaminants, and biological and mineral content. So this is also partially supported because it's discovered that there is a low R square value which suggests that other factors like temperature and biological activity may have a greater influence than the other factors that were listed in there. So we proceed to the discussion. So to discuss about the first hypothesis, why we support it. So we got the p-value less than 0.05, which is directly reject the null hypothesis and we support the hypothesis. We also discovered that the neutral pH here has a higher range, has a higher portability rate than other pH range. So the next hypothesis is we want to see the comparison with the subset portability rates. So this is the list of the portability with the condition, and then we can see the portability rate for each one. We see that the p-value for the highest portability rate, which is the neutral pH and low sulfate, is 0.4594 and its p-value is less than 0.05. So we can support this hypothesis. But however, we want to test for the lowest portability rate too. And this is for the low chloramines and neutral pH. So we got very way larger than 0.05. So which means that we cannot reject the null hypothesis. No significant difference in portability rates too. So this is why we are partially supporting this hypothesis because it's varying effect for each contaminants. Fluctuations in pH levels are influenced by temperature, contaminants, biological activity, and mineral content. So you can see the linear regression model here in the left side. There are out two square detected here. So this we can identify that significant predictors of pH are hardness, solid square, chloramines, organic carbon, while turbidity has a marginally significant effect. So as mentioned earlier, low R square suggests that temperature and biological activity not included in the model may play a vital role in affecting pH. So we also find out that there's no significant multicollinearity and our model are available. So for this figure, we only change a little bit, remove the non-significant predictors such as the sulfate conductivity, and then we fit to improve the interpretability. So this is the relationship between hardness and pH on the right side. You can see it's gradually increasing for the blue line. However, we can conclude that this is partially supported because the low R square value pointing out that other factors not included, such as temperature and biological activity in the model, might play a more important role in influencing these fluctuations of the pH. So that's all for me. Thank you.
And lastly, for our future work that we could do is to address the static nature of the current dataset, future project could integrate IoT device for real-time monitoring, like using IoT-enabled sensor for continuous water quality measurement so it can provide dynamic data for real-time insight into water quality fluctuation. Another improvement that we can do is implementation of multivariate analysis technique like principal component analysis, which simplify complex dataset, revealing underlying pattern and correlated variable. Second, multivariate regression, which analyze the combined effect of multiple water quality factor, and canonical correlation analysis, which examines relationship between environmental factor and water quality indicator. This is because it enables comprehensive insight by exploring the interdependency between various water quality parameters and providing a more holistic view of how different factors collectively influence water potability. And that is all from us. Thank you.
That's all from us. Thank you all for your attention and interest in this critical topic. Assalamualaikum warahmatullahi wabarakatuh.